fire safety deserves top priority. Every day, dozens of fires rage in the Benelux, causing the death of dozens of people and injuring thousands. Burns are some of the most serious injuries a person can suffer. The damage from the fires costs hundreds of millions of euros every year. More than half the companies who've had a big fire go bankrupt within 3 years. Moreover, every fire generates harmful consequences to the environment. The images in this film show the possible effects if the fire safety of the insulating materials used are not taken into sufficient consideration. These materials can contribute significantly to fire propagation due to the release of combustible gases, smoke development, and falling burning droplets. In this film, we'll show you the differences in fire reaction and fire behavior on the basis of objective scientific tests. As you'll see, the right selection of such insulation material can literally be of vital importance. Since the introduction of the new Euro fire classes on the 1st of February 2002, a clear classification system has been developed for building products for the entire European Union. The new method can be used to test all products for their fire behavior in the same way. 4 small-scale fire tests have been designated in order to arrive at the Euroclass classification. The SBI, or Single Burning Item Test, the Bomb Calorimeter, the Small Flame Test, and the Non-Combustible Test, or ISO Furnace Test. The small-scale SBI test is derived from a much larger fire test, the realistically dimensioned room corner test. In this test, a room is covered with the products to be tested. It examines when flashover takes place. Flashover is a very high-temperature fireball particularly feared by firefighters. The European classification fire tests are carried out, among others, by the Warrington Fire Ghent Test Laboratory. This test laboratory is a spin-off of the University of Ghent in Belgium. The laboratory has an established reputation and is an authority in the field of fire safety in Europe. For this study, Rockwool tested basic insulation material, Rockwool, EPS and PIR alu, as well as sandwich panels. Before the fire test took place, various zero measurements were taken without test sample. Let's take a look at the test sample fire measurements. In the room corner test, about 30 square meters of insulation material is affixed in a room. The sandwich panels, or the insulation material, are exposed to a 100 kilowatt flame in a corner of the test room for 10 minutes, followed by exposure to a 300 kilowatt flame for 10 minutes. The capacity released, the smoke production and the temperature are measured over time just above the burner at 7 different locations on the ceiling, as well as at various heights in front of the doorway. In addition, pressure and radiation are measured at the floor level, and radiation is measured at a distance of 1 meter in front of the doorway. Any products that do not result in flashover during a 20-minute period in the room corner, the reference test, are products that do not or that barely contribute to fire propagation. Products in fire classifications A1 or A2 always comply with this. If flashover does occur, the phase in which this happens is checked. Next, the small-scale fire tests used to establish the Euroclass. The SBI is designed to determine classifications A2, B, C and D that simulate a starting fire, for example, in a burning waste bin. The surface of the material to be tested is exposed to a 30 kilowatt flame for 20 minutes. The effect of the combustible flue gases on fire propagation and flashover is not taken into consideration in the SBI test. The oxygen consumption and the smoke and CO2 production are checked. Oxygen consumption is measured because it's proportional to the capacity released in a fire. For the so-called zero measurement, the temperature is measured at 3 different points near the corner at 1.5 meters above the burner, in the corner, and on both sides 20 centimeters from the corner. The radiation is also measured at a 45-degree angle at a height of 1.6 meters. This small flame test is used for product classifications B, C, D and E. It's used to test the combustibility of a material by means of a candle flame. It's determined whether a product ignites easily and quickly and whether the fire then spreads quickly. The zero measurement takes place by measuring the temperature change at the surface of a non-combustible base. The flame is directed to the bottom at the cutting edge. Measurements are taken at 2 centimeter intervals up to a height of 15 centimeters. During the test involving the test sample, the flames may not spread further vertically than up to the mark at a distance of 15 centimeters from the point where the test flame is applied. The bomb calorimeter is used to measure the energy content of products. An accurately measured amount of product is ignited in a hermetically closed small cylinder or bomb at a pressure of 30 bar using pure oxygen. The combustion value or energy content of the product is measured by registering the temperature increase of the surrounding water jacket. This combustion value is expressed in megajoules per kilogram and must remain below a certain value to comply with Class A1 or A2. The zero measurement does not take place in this test, since doing so would require test material. In order to measure the incombustibility of a material, the so-called ISO furnace test is used. This test simulates a completely developed fire at the moment of flashover. In this test, a small sample of a material is exposed to a temperature of 750 degrees Celsius in a furnace for 60 minutes maximum. The extent of temperature increase, weight loss and ignition time at this temperature determine the incombustibility of the material. The zero measurement here takes place by measurements at 3 places in the furnace without a test piece for a 1-hour period. Temperatures are measured at 1 centimeter from the wall, in the middle of the furnace at half the total height, and on the surface of the test sample. What's striking in this test is the increase in temperature in the test furnace. For Rockwool, the temperature in the furnace increases by 18.08 degrees Celsius. For PIR, this increases 154 degrees Celsius. The reason for this is that this plastic burns as a result of the sudden release of flue gases that cause ignition. EPS shrinks when it burns. The temperature increases only slightly due to the chimney effect that occurs in the process. Furthermore, the test results show that plastic insulation materials lose 100% of their weight and burn up entirely. Thus, PIR and EPS burn up completely at 750 degrees Celsius and are therefore combustible. Rockwool has an ignition time of 0 seconds. This means that no flames are visible at 750 degrees Celsius. Moreover, the weight loss of Rockwool is very limited in the ISO furnace test. 3.53%, which is due to the binding agent in the Rockwool. The insulation material hereby amply complies with the criterion for classification as a non-combustible material. This small flame test shows that Rockwool does not ignite at this low temperature load of a maximum of 180 degrees Celsius in the zero measurement, identical to a candle flame. PIR carbonizes when exposed to this low temperature, and EPS shrinks away from the fire. On the basis of the small flame test, we can conclude that PIR and EPS are not easily combustible at this relatively low temperature due to the use of fire or flame retardants. However, these fire retardants do generate unpredictable reactions to fire that's progressed further with a higher temperature load, such as in the room corner. Since the energy content of Rockwool is less than 2 megajoules per kilogram of product, Rockwool is non-combustible. So this insulation material no longer has to be incorporated in the fire load calculation. The measured energy content of PIR is about 30 megajoules per kilogram, and that of EPS more than 40 megajoules per kilogram. PIR and EPS are thus combustible and contribute to the total fire load. The temperature load right at the top of the tested materials is 300 degrees Celsius in accordance with the zero measurement at a height of 1.5 meters. This concerns the first phase of a fire before flashover occurs. At this temperature load, PIR creates a double temperature development in comparison with Rockwool and EPS. The temperature developments are closer to each other for the sandwich panels due to the protective effect of the metal skins. After conclusion of the test, the Rockwool sheet is still entirely intact. A large part of the insulation of PIR and EPS has burned away. Rockwool, uncovered or sandwich, barely contributes to smoke development, while PIR does. The steel cladding protects the PIR sandwich from direct contact with flames. Because of this, the temperature load is too low to gasify and ignite the PIR insulation. EPS already melts or burns at a low temperature load. The EPS melts because of the metal skins on the sandwich panels. As long as the EPS is enclosed, the temperature, and thus the smoke development, remain low. The following fire properties of materials are of great importance for proper evaluation of fire propagation risks. Calorific potential, the energy content of the material used, also called the fire load. The capacity released and the speed with which this takes place. The fire reaction speed and the start of secondary fires in places that were not taken into account. The contribution to the temperature development. The chimney effects and ensuing pressure differences as a consequence of the heat produced by the hot, non-combusted flue gases. Fire propagation due to scattering of non-combusted flue gases and burning droplets. Fire propagation due to heat radiation where ignition takes place with no flame contact. The SBI only provides information about fire reaction at a low temperature load of about 300 degrees Celsius at 1.5 meters above the burner in accordance with the zero measurement. The room corner provides information about fire reaction at higher temperature loads up to about 1000 degrees Celsius at 2.4 meters above the burner in accordance with the zero measurement. Thus, the room corner test is a better representation of what actually happens in a fire that's developed. The room corner reference test, EN 14390. In this test setup, the time flashover occurs determines how quickly a product will start contributing to the fire. If it happens within 2 minutes, the products are designated Fire Class E. If it happens in the period between 2 and 10 minutes, the product is in Class D. While the capacity growth must also remain below a certain value, less than or equal to 7.5 kilowatts per second. At a nearly identical escaping flue gas temperature for PIR and EPS, the radiation levels differ significantly. The EPS test was halted prematurely due to controllability issues. Rockwool is practically identical to the zero measurement. Products that result in flashover after 10 minutes in the second phase of the test using a flame with a capacity of 300 kilowatts make a limited contribution to fire propagation and are designated Fire Class C. The capacity increase during the fire is also checked. This must be less than or equal to 1.5 kilowatts per second. The capacities released for PIR and EPS sandwich panels are substantially higher than those for Rockwool sandwich panels. Products that do not result in flashover during the 20-minute room corner test, or in other words, do not reach a fire capacity of 1000 kilowatts, are products that do not or only slightly contribute to fire propagation. These products are Class A or B. Flashover occurs within 20 minutes in the room corner area for both PIR and EPS, with or without protective steel plating. This means that these products will contribute to the further development of a fire. The graph shows that the released capacity and radiation level in particular increase for PIR within a short time. When using 30 square meters of PIR in a room corner, a large capacity is released, more than 2,000 kilowatts in 2 minutes, as is a radiation level that's many times more than the maximum permitted level of 15 kilowatts per square meter. All building products in the EU member states must eventually be provided with CE marking. The CE marking is a type of product label or conformity mark that indicates that the product in question has been tested in accordance with the European specifications. One of the properties stated on the CE marking is the Euro class for fire reaction. Since the 1st of January 2009, sandwich panels can also be provided with CE marking. CE marking will be mandatory for sandwich panels from the 1st of October 2010. The legally required class of the material behavior in case of a fire is the Euro class. The Euro class assigned does not show the entire fire hazard because the Euro class is determined by carrying out small-scale tests. The more extensive room corner test was the basis for this. This larger-scale test gives a more complete picture of reality, especially also when the fire is bigger. This also applies if a product is classified in the Euro class under the condition of certain assembly and processing regulations. Sandwich panels and roof structures with combustible insulation, for example, can pose a higher risk in practice than one would assume on the basis of the Euro class. A large number of scientific publications point to this difference. The SPI mainly tests the outer surface, while the room corner also tests the material behind the outer surface. For example, the combustibility of the insulation behind a steel plate. Heated plastic insulation will release combustible gases, causing the steel plate to be deformed. Combustible gases escape through the joints. On roofs, these gases initially escape from the heated side, which is inside the building. The combustible gases enter the building not only due to sloppy installation, but also via extra screw holes and pipe lead-throughs. Thick smoke will accumulate at the top of the room and after sufficient heating will abruptly start igniting. This is the notorious flashover. Another problem with the SPI test is that it only tests vertically. So this test is not representative for a roof. Just think of the falling burning droplets. In addition, only a fire from the inside is simulated, while the source of a fire on the outer wall could, for example, also be an adjacent building or a fire in a stack of pallets placed against the outer wall. The room corner reference test is based on EN 14390 and consequently may deviate from the Euro class in which it's officially categorized. The room corner test results show that Rockwool products are differentiated from PIR and EPS insulation in this test due to the incombustibility of the insulation material. Since currently the construction regulations do not always show such a difference due to the omission of large-scale tests, opting for Rockwool insulation means opting for a significantly lower fire safety risk in practice. For fire safety engineering, knowledge of the actual fire behavior to be expected from the building shell is essential if the fire expansion and smoke production are not to be underestimated. In practice, combustible insulation is increasingly sealed up in the construction components. In general, calculation models that are supposed to predict fire development do not take this into account. If this is the case, the use of these combustible insulation materials is irresponsible. The extent of heat radiation in a fire is calculated by the sum of the permanent and variable fire load. Burning flue gases are not only discharged vertically, but also in other directions, sometimes almost horizontally, due to the wind velocity effect. The extent of heat radiation on adjacent roofs and outer walls thus depends on the weather and can end up far above the limit value of 15 kilowatts per square meter. Because of this, the surface of roofs and outer walls of adjacent fire compartments and adjacent buildings can start to ignite, and plastic insulation materials can burn. Such a fire scenario is described in European Standard EN 1187 Part 3, for instance. Rockwool in exterior walls and roofs stops the heat radiation of a fire in the building, giving the fire brigade more time to prevent the fire from spreading to adjacent compartments and adjacent buildings. A possibly wrong choice of insulation material or other construction materials may have far-reaching consequences in view of the new Housing Act. To wit, the expansion of the Housing Act in 2007 by the principle of care placed a direct additional responsibility on the owner, builder and user of a building for the effect of a building on the safety and health of users and people in the vicinity. In short, the owner must ensure that a building complies with the Building and Use Decree. Acting in violation of the principle of care may even be a criminal offence. Designers, principals and building owners must remain alert when assessing the fire safety of buildings. So choose certainty. Choose Rockwool, made by Rockwool. Fire safety deserves top priority.